All right, so we're going to keep on in our video section here by continuing on in chapter 6. Today we're going to be doing section 6.5, which is titled Least Squares Problems. All right, so as I mentioned at the end of the last video, these next couple of video sections that we're going to end this class with are going to talk about approximations and how we use vector operations, orthogonal projection, all that stuff into approximation ideas. So the idea here comes from that inconsistent systems arise often in applications of different varieties. When a solution is demanded and none exist, the best one can do is to find a vector x that makes a times x as close as possible. So essentially, these first couple sentences are saying what we already know. There is a chance that you will get an inconsistent solution when you're trying to row reduce in an augmented matrix. But what if you really want the best x possible? So what vector x gets you the answer as close as you can to generating the vector b after multiplication? Well, when that comes into the idea, obviously you want the distance between vector b and the vector ax to be as small as possible, which you can find by taking the norm of b minus ax, because this indicates that you have the best approximation possible. So can we find a vector x that minimizes this error between b and ax? Well, let's define something here. So let's assume that A is an m by n matrix and B is a vector in the nth dimension. Then we can define a least squares solution of the matrix equation as the vector x hat, such that the following always is true. So if we were to ever find the magnitude of vector b minus vector ax hat, it will always be less than or equal to the magnitude of the vector b minus a times x for every other x in the nth dimension. So using my visual down here to represent what this definition says is that while there are infinitely many x's that you can multiply a by, now you'll notice here, this vector b is not in the column space of a because we know that it's an inconsistent solution. But can we actually find what we call a vector x hat that will minimize the distance between the column space and the vector b that you want? Like I said, obviously there are infinitely many combinations here. We don't care about all of those. The question just becomes, where do we find or how do we find this vector x hat? All right, so here's the theorem that allows us to do that. And you're going to see two different formulas here. So the theorem says the set of least squares solutions of the matrix equations coincides with the non-empty set of solutions of what we call the normal equation. So what you'll notice here is that we haven't seen the normal equation yet, so we're going to define it for the first time. We have our matrix equation. To make a matrix equation a normal equation, you need to left multiply both sides of the equation by A transpose. So you will notice there's the AX, there's the B, and on the left-hand side of each side of the equation, we are multiplying this by A transpose. Now, why do we do that? Because that brings up the next line here of the theorem. If you were to solve this for vector x, so the solution of this normal equation that we are going to define as x hat, which is our least squares solution, to get the A transpose A to the other side, you need to multiply both sides by A transpose A's inverse. Doing that will cancel the A transpose A on the left and will leave you with the equation that x hat will equal A transpose A's inverse times A transpose B. So now we kind of get back to the reason of why we chose A transpose. Remember from what we've learned so far with least squares, A is defined as an m by n matrix. So if A is there, you can't take the inverse of A and multiply it because you can't find the inverse of a non-square matrix. So instead, if we multiply A transpose times A, This is the same thing as taking an n by m, multiplying it by an m by n, which we know will generate an n by n matrix. And that then allows us to do the inverse part and find x hat. So you see two equations here. If you're ever looking for a specific x hat, or what we will usually call the best approximation of the matrix equation, you will use the formula that you see in the green box. Now, as we saw on the last picture, there are infinitely many least squares solutions that exist there. And sometimes, depending on what you're working on, you may be asked to describe all least squares solutions. So my recommendation is, if you're ever asked to describe all least squares solutions, we'll use this top matrix or this top equation as well, and it's going to involve us doing some row reduction. The reason we want to use row reduction for the descriptions, because you're going to probably end up getting infinitely many solutions, and we know how to write that in parametric vector form. Versus if we're just looking for a unique, specific x hat, we will go directly to this bottom equation in order to do that. So let's look at our first problem here. If I give you a matrix A and I give you a vector B, I want you to find a least squares solution of the matrix equation AX equals B, and then I also want you to find the least squares error, which we defined as B minus AX hat. So since it's asking for a least squares solution, that's singular there, we're going to use the formula that X hat will be A transpose A inverse times A transpose B. So in order to compute this formula, the first thing we're going to have to do is find what is A transpose A. So let's begin with that. If I transpose A, that's going to be 2, negative 2, 2, 1, 0, 1, and then times A, which is just the original matrix A. Multiplying these together by the row column rule is going to end up giving us a 2 by 2 matrix. So if I take the first row and multiply it by the first column, you should get 4 plus 4 plus 4, which is 12. First row times second column is going to give me 2 plus 0 is 2, and then 2 plus 2 is 4. All right. Then if I move to the second row times each column, one thing you're going to notice here is that when you do the second row times the first column, it's the exact same as the first row second column that you just did. So you should end up getting the same number, the 4 again. And then if I take row 2 times column 2, you should get 2 in that case. So there's A transpose A. Now you want to find its inverse. So A transpose A's inverse, since it's a 2 by 2, we can use our algorithm formula. That would be 1 divided by the determinant of A, transpose A, which would be 24 minus 16. Remember, you're going to interchange the main diagonal and you're going to negate the non-main diagonal. So this ends up giving us 1 over 8 times 2, negative 4, negative 4, 12. And so if I multiply everything by an eighth, I will end up getting a fourth, a negative 1/2, a negative 1/2, and then a 3/2. And so that gives me my A transpose A inverse part. So now to fill in the gap, when you go to find X hat here, you're going to take the inverse you just found. So 1/4, negative 1/2, negative 1/2, 3/2, and we're going to multiply that by A transpose. And then you're going to multiply that by the vector B that we're trying to get as close as possible to. All right, so to try to avoid avoid using these fractions until I have to, what I'm going to do is I'm going to multiply the second two matrices together first. So that will give me 1/4, -1/2, -1/2, 3/2. And so if I multiply this 2 by 3 times this 3 by 1, it should give me a 2 by 1. So I'm going to take this row times this column. That will give me -10 minus 16 is -26. And then -26 plus 2 is -24. And then second row times the same column should be -5 plus 4, which is -4. And then if I multiply these together, a 2 by 2 times a 2 by 1 should give me another 2 by 1. And so if you need to use your calculator here, it might be helpful. I'm going to try to number crunch this the best I can. So row 1 times this should be, that's going to be -6 plus 2, which is -4. My pen will come back. Come on, pen. There we go. Sometimes it just doesn't want to work. And then second row times that column would be 12. And what's that going? 12 minus 6, which is 6. I may have done that wrong. -1/2 times -24 is 12. 3/2 times -4 would be -6 in this case, because that's -12 divided by 2. So that should give you 6 here. Sorry, I had to do a little mental math without a calculator in front of me. All right, so this is what we claim to be our least square solution in this case. All right, so I am double checking. I think I made a mistake because that doesn't add up to what I have here. Hang on, let me double check my work. Like I said, it happens to the best of us. Sometimes you get messed up here. I'm gonna double check. Let's see, that's -10, -26, -24. That looks good. 101 is -5 plus -4. Okay, so that's got to be good. Let's double check our inverse here. That is 1/24 minus 16. All right, so that looks good. Flip those, negate those. Looks good. 1/8. It's going to be 1/4, -1/2, -1/2, 3/2. So that looks fine. That would be -6 plus 2 more is going to be -4. And that is 12 minus 6, which is 6. Did I find my A transpose A incorrectly? I'm going to feel really dumb if I did that. So that's 4 plus 4 plus 4 is 12. All right, and then 1, that's 2 plus 2, which is 4. 2 plus 2 is 4. 1 plus 1, no, that all looks good. Something is incorrect here because it's not working out correctly. -4, 6. Apologies, guys. I'm going to pause the video real quick and figure out where I screwed up because I don't want to keep y'all sitting here. So hang on one second. Sorry about that, y'all. I had a moment there for a minute. I forgot that we're doing a least squares section. This is not going to work out exactly. So I apologize. I went off on a little tangent there trying to think I messed up. So we're good. The problem I had was in my mind, I was thinking, oh, that's got to be the exact solution, but I forgot we're doing least squares error. So you're not going to find an exact answer. So my apologies there. So we have our x hat, which is going to be our least squares solution. So now we want to find the least squares error, which means we are going to take the magnitude of b minus ax hat. So I first need to compute what is b minus ax hat, and then I'm going to find its magnitude. So in this case, b is going to be -581, and I'm going to subtract from that my matrix A times the x hat we just found, and let's see what we get. So that's going to be -581 minus a 3 by 2 times a 2 by 1 should be a 3 by 1. So each row times the column should be -8 plus 6, which is -2. 8 plus 0 is 8. And then -8 plus 6 is -2. Subtracting these two vectors from one another, you should get -3, you should get 0, and you should get 3. So from here, you want to find the magnitude of this vector you just found. So coming down to the next slide so I have more room. The magnitude of b minus a times x hat is going to end up being the square root of 9 plus 0 plus 9, which is the square root of 18, which does break down into 3 square roots of 2. So if you were to map this and actually draw out this idea, we just found that our vector b is actually 3 root 2 units away from the subspace that is made up of the columns of matrix A. Once again, apologize for the little mix up there. I just had a little mental fart there for a minute as I was going through that. But like I said, we're not going to find exact solutions today in this section. It left my mind as I was making these videos today. All right. So now that we've learned how to find the exact unique solution or the least squares error, what if you're trying to describe all the least squares solutions of a matrix equation? So here I've given you a matrix A of the 4x3 variety, and I've also given you a 4-dimensional vector B. So what I want to do is I want you to find an x hat as a description of all of them, which means it's probably going to have infinitely many solutions. So if you go back to a couple slides ago, when you want to find and describe all the solutions, you need to take A transpose A times X is equal to A transpose B. So no inverses this time, but you still have to find 2 things for me. You've got to find your A transpose A, and you've got to find your A transpose B to set up your augmented matrix. So down here below, we're going to find A transpose A first. So that'll be 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1 times the original matrix A. So a 3x4 times a 4x3 is going to generate a 3x3 matrix. So if I do the first row times all 3 columns, you should get 4, 2, 2. Then if I take the second row and multiply it by all 3 columns, you should get 2, 2, 0. And then if I take the last row times all 3 columns, you should get 2, 0, 2. And so that is A transpose A. Over here to the right, if I have a little bit of room, I'm going to find A transpose B next. So take the same A transpose. We'll write a little smaller so I can try to squeeze it in here. And we're going to multiply this by B. So in this case, a 3x4 times a 4x1 should give us a 3x1. I'm going to take each row of the matrix times the column there. So row 1 times the column should be 4, 6, 14. The second row times the column should give us 4. And the third row times the column should give us 10. So now that I have both bits of information, I can now set up my augmented matrix, beginning with A transpose A, which is 4, 2, 2, 2, 2, 0, 2, 0, 2. And we augment it with A transpose B, which is 14, 4, 10. Now, before I even begin this problem, the first thing I actually notice is that every single number in this entire matrix is divisible by 2. So this is a little bit unorthodox. I'm going to half the entire matrix just because I want to make all the numbers as small as possible. So that would be 2, 1, 1, 7, 1, 1, 0, 2, and then 1, 0, 1, 5. That looks a lot better to me. So now to get this into reduced echelon form, I am going to interchange row 1 and row 2. That's just my choice. So we'll have 1, 1, 0, 2, 2, 1, 1, 7, 1, 0, 1, 5. So then I'm going to take row 2 and subtract 2 row 1s. And I'm going to take row 3 and subtract row 1. So the first row remains the same. Row 2 is going to become 0. 1 minus 2 is negative 1. 1 minus 0. And then 7 minus 4 is 3. Followed by row 3 minus row 1 is 0, negative 1, 1, 3. As you can see, the bottom two rows become exactly the same. So I know that by my ideas from this class that the bottom row is going to go to all zeros, and we're going to leave everything else the same. And then to put this into reduced echelon form, I need to take row 1. All right, and I am going to add row 2 to it. So that will make the top row become 1. 1 plus negative 1 is 0. 0 plus 1 is 1. And 2 plus 3 is 5. And now that I've done the top row, now after I've done the addition, then I'm going to take row 2 and negate it. So 0, 1, negative 1, negative 3. Please keep in mind, I did the addition first and then I did the negation. You could have also done the negation first and then it would have been a subtraction problem. Just make sure you're doing one step at a time. So this tells me that x1 plus x3 needs to equal 5. x2 minus x3 is negative 3, with x3 being my free variable. And so thus x1 needs to equal 5 minus x3. x2 needs to equal negative 3 plus x3, with x3 being a free variable. So remember, we're describing every solution, so it makes sense that we're going to have infinitely many solutions here. So our vector x hat can be described as the coefficient vector, which we found to be 5, negative 3, 0. And then we add to that the free variable vector with x3, and based on your coefficients, that should be negative 1, 1, 1. And this is the description of every single free variable, every single least square solution that exists. And so there are infinitely many of them. We don't do the description very often, but it's a necessary thing to kind of see that there are more than just one. Now, obviously, if we want the best one, we would go back to the previous slide and do our formula for x hat. All right. So now that we've kind of talked about the basics of least square solutions, there is a special case of it. We could have actually done least squares in the last section, but I wanted to save it for this one to cover all the bases at once. So a little extra note here. When the columns of a matrix A are orthogonal, then we can use the orthogonal projection of B onto the column space of A to find a least square solution. So how do we use orthogonal projection that leads to least squares? Well, let's look at this example and I'll kind of talk you through it. Example number 3 says, find the orthogonal projection of B onto the column space of A and the least square solution of the matrix equation. So in this example, we're going to think of the two columns of A as being A1 and A2, and obviously we're trying to project B onto the column space, which if you remember from the last video, whatever vector you're trying to project onto the column space, that's the vector hat you're trying to find. So in this case, we're trying to find B hat. So using our formula from the last video, since we have two vectors here, this would be B dotted with A1 over A1 dotted with A1 times A1 plus B dotted with A2 times A2 dotted with A2 times A2. So that is our orthogonal projection formula from the last video. Now remember, in case you can't remember, orthogonal projection, like it's set up here, is only done if the vectors are orthogonal to each other. So if you didn't check it already, for those who are trying to do it along the way, if you dot A1 and A2, that is 5 plus 3 minus 8, which is 0. So we are allowed to do this. So computing all these values, If I dot B and A1, that would be 4 minus 6 plus 6 over 1 plus 9 plus 4 times A1, right? Plus B dotted with A2. That is 20 minus 2 minus 12 over A2. Let's see, 25 plus 1 plus 16 times 514. All right, so if we simplify this, that first one's going to end up being 4 on top and 14 on the bottom. So that becomes 2/7 times my first vector. Let's see, that's going to end up being 6 on top and 42 on the bottom. So that's 1/7 times my second vector. So multiplying through by my coefficients, that's going to be 2/7, 6/7, and -4/7, plus my last vector, which is 5/7, 1/7, and 4/7. Adding those together, 2/7 and 5/7 would just be 1, 6/7 and 1/7 is also 1, and -4/7 plus 4/7 is 0. So this is our projection. So this is the orthogonal projection of B onto the column space of A. Now, going back to the original idea on this slide, the note I gave y'all is that by finding the orthogonal projection, you also found a least squares solution in this case. So remember, your least squares solution in most problems is you're trying to find the vector x hat. Remember, your x's are the coefficients that you're multiplying by. So what are you multiplying A1 and A2 by in order to make this work? Well, in this case, you are going to end up doing 2/7 and 1/7 as your coefficients that you're multiplying by. So in this case, 2/7 and 1/7 would be the values of your least squares solution. And that's what x hat is going to be. If the problem had not asked me to find the orthogonal projection all the way through, we could have just stopped and said x hat has to be this solution. Versus it asked me the orthogonal projection, so we got an answer of 110. So your projections, this B dot A1 over A1 dot A1 and B dot A2 over A2 dot A2, those are the components of your least squares solution, but that is only true because you were allowed to do orthogonal projection. All right. And so my last thing that I want to cover in this least squares solution video is bringing back the idea that I ended the Gram-Schmidt process video with, and that was QR factorization. So a new theorem here. If you are given an M by N matrix A with linearly independent columns, if we let A equal QR be a QR factorization of A, then for each B that exists in the nth dimension, AX equals B has to have a unique least squares solution given by the following formula. So X hat can be found by taking the inverse of R times Q transpose B. So that is the unique solution, or I should say the unique least squares solution of the matrix equation. So once again, AX equals B cannot be solved. All right, that's why it says for each B, because it doesn't really matter. There can be an inconsistent solution. For any B you pick, if you can find A into its QR factorization, you can use the Q and R to find X hat initially. Now, this is a very direct formula. Some people prefer to use row reduction, and that's perfectly fine. If you want to do row reduction, you've got to move the R inverse back to the other side with X hat. So I would multiply both left-hand sides by R. And so we could use the row reduction technique of Rx hat equals Q transpose B. Now, a question I get from students once in a while is, well, how do I know which one's better? Here's my idea, or here's my thought. It all hinges on R inverse. Obviously, finding the inverse of a matrix can be very daunting the bigger the square matrix is. If R is a 2 by 2 matrix, not challenging at all. We can find an inverse of that pretty quick. If R is 3 by 3, that's not as much fun anymore. And then 4 by 4 and higher, I definitely don't do it. So if R is a bigger matrix, I see most students will prefer to not do the inverse of it and just go straight into row reduction. But you always have that first formula to fall on if you are comfortable finding R inverse. Either way, you've got to find Q transpose B on both of these. So we'll play it by ear when we do these problems. So here's my example for you. Now, I am never going to make you do the QR factorization and then do the least squares, at least not right now on your problems at the end here, because that's so many spots you can mess up at that that's not what I'm trying to test you on. So I would probably give you a separate problem to show me you can do QR factorization. And then I would do something like this, where I give you the QR factorization and your job is to find a least squares solution. So in this case, A is a 4 by 3 matrix, and you can see that I have already broken it down into the QR factorization for you. Your job is to find a least squares solution of AX equals B. Now, the first thing I notice is that R is a 3 by 3 matrix, and why, yes, that doesn't seem too hard to find the inverse of it. Typically, my personal preference is I just go straight into row reduction if it's bigger than a 2 by 2, but I do know that some of y'all will like to do the inverse, so you can do it that way. I am going to choose to do this formula. I'm going to do R times X hat equals Q transpose B. Excuse me. So to set up this augmented matrix, I still have to find one bit of information. I got to find Q transpose B. So over here to the left, I'm sorry, I guess y'all's right, Q transpose B. So if I transpose this 4 by 3 matrix, we are going to end up with, let's see, that'll be 1/2, 1/2, 1/2, 1/2, negative 1/2, and then negative 1/2, and then 1/2, negative 1/2, 1/2, and then 1/2, 1/2, negative 1/2 that we're going to multiply by B. So still a little bit of work, whichever way you do this, because you got to do Q transpose B no matter what. So let's see, that is 3 by 4 times 4 by 1. So this is going to end up being a 3 by 1 column vector when we're done. So I'm going to take each row, I'm going to circle in the first one for reference, and multiply it by the column and simplify. All right, here we go. 3/2 and 5/2 is 7/2. 3 and 5/2 is 8/2. 8/2 and 7/2 is 15/2. 15 minus 3 is 12/2, which becomes 6. All right, middle row. That would be 3/2 minus 5/2 is negative 2/2. Minus 7 more is negative 9/2. Minus 3 more is negative 12/2, so that's negative 6. And finally, the last row, 3/2 minus 5/2 is negative 2/2. Plus 7 more would be 5/2. Then plus 3/2 would be 8/2. So that's going to be 4. Also, you have your calculator if you need it. Just take your time through that. Now that I have Q transpose B, I can set up my row reduction. So I'm going to take my R matrix, which I've already given you, 2, 4, 5, 0, 2, 3, 0, 0, 2, and I'm going to throw in my Q transpose B to make it augmented. So now my job is to put this into reduced echelon form. So a couple things you could do here. I'm going to take row 1 and subtract 2 row 2s to get rid of that 4 first. So that would be 2, 0. 5 minus 6 is negative 1. And then 6 plus 12 is going to be 18. 0, 2, 3, negative 6. And also, while I'm here, I'm going to go ahead and reduce row 3 or scale it by a half. So 0, 0, 1, 2. Before I scale anything else, I'm going to go ahead and finish getting rid of column 3 here. So I'm going to take row 1 and add row 3. And I'm going to take, I'm going to take row 2 and subtract 3 row 3s. So while the bottom row doesn't change, the top row is going to become 2, 0, 0, 20. And then the middle row is going to become 0, 2, 0. And then negative 6 minus 6 more is negative 12. Finally, scaling row 1 and row 2, I'm going to take half of row 1 and half of row 2 in this instance, which should give me 1, 0, 0, 10, 0, 1, 0, negative 6, and then 0, 0, 1, 2. So what you have just found is based on this, our x hat, or our least squares solution, the unique one, is going to be 10, negative 6, 2, based on the QR factorization of the original matrix A. So the vector x that makes A times x the closest to B as possible is the 10, negative 6, 2. So as you can see in this video on least square problems, we talked about how we started introducing approximations. Remember, the goal of this section was not to find an exact answer. The goal was to find a vector x that got us as close as possible and allowed us to minimize the distance or the error of our solution. In my last video, which will be section 6.6 next, we're going to move into one of the biggest applications where this applies. That's called regression. So regression is one of those ideas where approximations are abundant. So we're going to use this idea, and we will wrap this class up in the next video using applications of this idea.